Welcome everyone. Today we're gonna be presenting Plonky3 Rangecheck. And if you didn't check out our last session, the last one that we did was introduction to Plonky3, and also we covered a little bit of the Fibonacci implementation in Plonky3. Here's the link. So this is where you do the Fibonacci example. We cover the basics and then how it works, etc. all the way to the end. We gave a Fibonacci example. And then from there, we now want to introduce this concept called the Rangecheck. And then specifically how you can implement it in Plonky3. We gave out 4 examples in this tutorial, starting from easy all the way to the harder ones. Easiest will be the Mersenne 31. It's a very specific field that we use in Plonky3, and we're just using Mersenne 31 as an example. Also, same with BabyBear and Goldilocks. They're all fields that Plonky3 uses natively in the proving backend, but we're writing them in the front end, the circuit portion. And then we also have an improved version of the BabyBear. So this is the V1 that we're going to introduce. And then, but because it is a very basic implementation, there's a lot of room to optimize it. So we're going to introduce the optimized version as well. And what we're really trying to deliver is through this process, not only you're going to understand the Rangecheck concept itself, but also you're going to understand deeply on how to utilize Plonky3 to optimize your constraints, and most specifically, the idea of the degree in your constraints. And at last, I have a little bit of assignment where you can explore on your own. We're going to cover that in a bit. So first, let's start with introduction to Rangechecks. For Rangecheck, it is a fundamental operation in zero-knowledge proof systems. So in zero-knowledge proof, because all of the result has to be a definite, like static way of defining some of your limitations. And what we're doing in terms of checking whether a number is less than or greater than, we use these concepts called Rangechecks. And they allow us to prove that a value sits within a specific range. And also we're not revealing the actual value itself. So that's where the zero knowledge portion comes into play. And this is crucial for a lot of applications. For example, privacy preserving finance transactions, secure voting systems, age verifications, and then salary range. And of course, the current most used sort of a Rangecheck implementation is ZK EVM and ZK VMs. And for those, and they're specifically used for checking whether an input or a value is within a range, a field range that is supported by that VM. So in this example, we're going to cover the BabyBear field. It's inspired by the SP1 BabyBear field Rangecheck implementation. So we're going to cover that too. All right, so next we're going to talk about the Plonky3 way of implementing Rangecheck implementations. And we're going to divide them in 4 chapters or 4 sections. First, we're going to cover the Mersenne 31 implementation. This is going to be the simplest implementation of the series, and implementing the Mersenne 31 field Rangecheck. And then follow up, we're going to have a 32-bit Rangecheck, which is the BabyBear one. And then this one, Goldilocks, is 64 bits. We're going to also explore that too. And from this simple all the way to top, the prover complexity actually becomes much higher because there's way more variables to consider from the simplest all the way to the Goldilocks. And then we're going to cover this BabyBear V2, where we're going to say, hey, even though the complexity increases, but there are some clever tricks that we can use to keep the prover cost, instead of linearly growing, we try to optimize it so that the prover cost doesn't increase with the complexity of the constraints. All right, let's dive in. And also these examples, these stats ran on M2 Pro Max, MacBook Pro. That's on my computer. All right, first, we jump into the Mersenne 31 Rangecheck. So Mersenne 31, if you're not familiar, it's basically a 31-bit numbers. Or in a CPU way, we just say it fits within the 2 to the 32 bits, that word size. But we're only using up this 31-bit, 2 to the 31 bits, and subtract 1. So the number will look something like this. Here, this is this table that I've listed out for you. In the 0 row, this is the actual input. So we have 0 at the beginning because the 32-bit, this is the big endian form. And the most significant bit is the 0th bit. and the least significant bit is going to be the 31. And the very top one is going to be 0 because it's only 2 to the 31 bits. And then we subtract 1. So we get all the 1s in the back all the way to the least significant bit. All right, and in this Plonky3 program setting, we're going to be using the Plonky3 backend. It's going to be the Mercine31, KitKat 256, and then Circle PCS. If you're not familiar what these means, it's because probably you missed out the last one. But basically, we can take a look at the code. Mercine31. So these are the constraints that we can pass for now. And then this is the execution trace. This is the Plonky3 backend setting, this whole thing, all the way to here. And as you can see, what we're using for Plonky3 backend, in this example, we're using a Mercine31 field. We're also using KitKat 256 hash functions for our Fry protocol. And some of the configs, we're not going to cover it in this class. We're going to cover these in depth in the future classes because this is more advanced. So no rush on that, but just so you know, these are a template that we provide. And most of the time, all you need to change is some of these numbers to configure. Numbers of queries and blowout vectors depending on your degree of the constraints, which we're going to cover in a bit. And also in this example, we're using Circle PCS, which is a type of PCS scheme that we're using. And there's this very specific requirements for Circle PCS is it has to use 4 rows of, it has to at least have 4 rows of execution trace. So that's, and remaining is just some of the remaining configuration. These are the start prover configuration. This is the error constraint instantiating process. And this is the execution trace. So all of these we're going to cover in a bit. So let's move on for now. Let's come back to here. So this is what it means. Like the Plonky3 prover backend we're using for this Mercine31 Rangecheck example is the Mercine31 field, hash is KitKat 256, and then Circle PCS. And there is a sort of extra requirements for Circle PCS is that for execution traces, Circle PCS provers, this backends, you have to have at least more than 4 execution rows to be able to generate proof. So I just added a whole bunch of zeros in the back, but they don't really serve anything. All right. And the only valuable row will be the first row. And then now let's jump into the execution trace generation. So we wanted to be able to create this matrix, this table, and we need to program that out, right? So it's gonna be this generate execution trace function, and then you throw in the value, which is the value that we're gonna break the value down into the bit decomposition, so into the binary form. What we're doing is just converting that decimal number into binary. So yeah, it's just simple binary operations, and if they're 1, you're pushing 1. If it's 0, you're pushing 0. It's in big endian format that I'm using. And then at last, we add 3 extra rows, so 3 times 32, 3 times of all the zeros. And then this row major matrix, this API will actually convert this one-dimensional matrix. This 4 times 32, so that's about 128 elements of the vector. We'll convert it into a 32 by 4. So this is where you define the width of the matrix. So this is how this API works. And by throwing them the 1D array, and then the width of the new matrix is going to be automatically calculate how tall is the matrix. And we'll return the matrix after calling this function. All right, now that we have the execution trace ready, we need to define the constraints. And this is the core of today's topic. For constraints in Rangecheck and Mercine31, there are several conditions to satisfy. Let's go through each one of them. So first is, in this execution trace that we saw, as we know, the very first bit, the most significant bit, the 0th bit, has to be 0, right? Because otherwise, if it's 1, that means the number is greater than the Mercine31 field, so it doesn't suffice. So it has to be 0, so this is one condition. And then secondly, because we're breaking the number down into binary, we have to make sure every single element in these columns, they're either 0 or 1, right? It couldn't be 2 because it's binary. So that's the second condition that we have to meet. And then the third condition is yeah, even though we broke down the numbers, but did we stuff them into the execution trace correct in a correct manner? We also need to check that. And how do we check it? We just reconstruct the value into the original decimal value and then compare it with the original value as the circuit inputs. We're going to cover that in a bit. And then remaining, this is where I'm just showing as an example, but technically the remaining 3 rows, it could be anything, right? But let's just be a little bit cautious and make sure all of them are 0. But I don't think it really matters, but that's what we're gonna do just for example, right? So we're gonna ensure all remaining 3 rows, they're 0. All right. So this is the constraint implementation. As you can see, at the beginning, what we're defining is the air constraint itself. Right, this is the air constraint struct on the object, and then we're defining the public inputs, saying, hey, if you want to instantiate this air constraint, you gotta pass in this input, and then this is the input that we're gonna throw it into the constraint to let it evaluate through. And same with the execution trace itself in the proof generation process. But regardless, we need this value, and this value will be used later when compared with the reconstructed value. And just a reminder, this is how the Machine31 looks like in binary and big endian form. The execution trace, the width of the execution trace is 32. We need to define that here too as well. So now here comes to the actual constraint checking process. Right? We first get the instance of the current iterator, and then we get the current row. This kind of works like per row iteration. So when it's on the first row, then the current row, the row slice this API, is going to return us the very first row. And the next row, which is the row slice 1, which is right after this row, is going to be the row that is below the current row. And it works like iteration. In the current iteration, it's in the first row. In the second iteration, if the current row is the second row, then the next row is going to be the third row, so on and so forth. First condition to meet, we need to make sure that in this first row, the very first element is 0. So that's what we're going to do. And we're using this when first row API. We're not going to use any other API because our value only exists on the first row. The remaining row doesn't matter. So we're going to use this when first row API and then just check if the 0th element, the very first element of this current row, if it's equal to 0. And this current row in this case, because it's when first row, so this current row would be the first row. So we're only checking it when it's on the first row. If it's on the second or third row, this line will not run. And then we go down to once this passes, then we go to the reconstructed values. We're going to reconstruct the value. In this case, we are initiating the reconstructed value itself. And then we're going to go through every single bit in that row. So in this current row, we're going to get the every bit and then making sure it's 0 or 1, right? This is the second condition that we need to meet, right? Every element in this second row has to be 0 or 1. This reconstructed by doing bit ship operation on top of the I, and then add all of them to the reconstructed value. And then at the end, what we're gonna do is if it's first row, right? If the sum process is using the current row's bits, and then we're adding all of those current row bits into the reconstructed value. And only if the current row is the first row, then we're gonna check if the value, the circuit input value here, this value is the same as the reconstructed value. So this is where we check against the third condition. The reconstructed value matches the input, the original value itself. And there are some lines that I skip in the process, which are the optional part. We're just checking if the sum of the remaining 3 rows is 0. And how do we do that? Is we do it indirectly. So what we do is first, we're getting the next row of the current row. So let's say we are currently on the first row, then the next row is going to be the second row. Second row is all zeros, right? And in this second row, what we do is first we create this sort of temp, the sum variable, and then we're just gonna add the next row's every single bits into this next row sum. And then we do that for the entire row. And as you can see here, we have this when transition instead of when first row. So when transition is actually called whenever there's in every single row of the iteration except the last row. So when transition is not applied when checking the last row iteration. Therefore, if you want to check the constraints in the last row, then you need to use the when last row. But in this case, when we're on the first row, we're checking if the second row sum is equal to 0, right? Here, this is when transition. Then we're checking the next row sum, the second row sum, if it's equal to 0. Then if we're on the second row, then the next row sum that we build out when we're on the second row iteration is the third row's sum, right? And we're checking whether it's 0. And then also, last but not least, when we're on the second row's iteration, the next row sum is going to be the sum of the third row, and it's also going to check if it's equal to 0 or no. And at the very last row, because when transition doesn't work, or it won't work in the last row, so when transition won't be called in the last row's iteration, unless if I specify another builder.when last row, then it's gonna do some extra work. So yeah, so that's a little, I guess, like indirect way of checking whether the entire row of the remaining 3 rows are 0 or no. So yeah, so that's the circuit for the Machine 31 range check error. And I do see one question. So your question was how to decide how many conditions to make for our constraints. For example, for this example, we have to make sure first bit is 0 and etc. How do the numbers of constraint affect the security? So that's a really good question. If I rephrase the question, it would means how do we come out with constraints, right? And how do we know when to stop? The answer is it really comes from experience and also just your security intuition too. There's no absolute way of saying, hey, my circuit is absolutely correct. But instead, it's better to just have more people to debug and then to audit it. So I guess that's the answer. And for coming out with constraints, I guess this is more so just, yeah, like after you review some of the examples, you're going to get some intuitions and then you're going to come out with it. But if you go into this very first lecture that I did give a tips on defining your error scripts or error constraints, right? So 4 things to keep in mind. First thing is to define a valid state transition, which is when transitioning from one row to the next row, is there any relations between the 2 rows, any elements to transition from one row to another, right? And also on the same row, is there some specific limitations that we need to check? Just like in this example, we're checking every element, whether if it's 0 or 1. So that's the second thing that we need to check, whether each element has a requirement on its own. And then thirdly, we'll be making sure that if this constraint has an initial state or no. If it doesn't, then you don't need a constraint. But if it does, then you have to define when first row-ish design to make sure the initial state is well defined. And in the Fibonacci example, the ending state was very clear. So we also needed to define that as well. But for some of the other constraints, maybe it's not necessary. But these are just 4 tips that you can just think about when you're writing your constraints. All right, so now we have written our constraints. We have written our execution trace here. So we'll go through the prove and verify, which is try to run it. All right, what we're going to be doing is cargo run. We'll use the release one because it's faster. And then we're using Machine 31, and then value is, and we can do 1,000. Why not? All right, so we can see this is the logging of the entire process. The proof generation process took about 21.5 millisecond, and then the verification took about 1.51 millisecond. So that's pretty fast, right? So there's a couple of other examples. Like for instance, we try to run it with 100. This is not the one using the release tag, so it's probably going to be a little slower because it has a lot of extra logging, extra debugging log, assertion, etc. So that's why it's taking up a lot of performance. But if we just run the same command in release, it's probably much faster. It's 100 millisecond, where in here is 1.73 second. Right? This is the debug mode, but it's super useful. So make sure when you're developing it, make sure you can use the debug mode first to develop it. And then we're gonna test the max number of Mersenne31, which is this in binary. So this is the number that's 0, 1, 1, 1, 1, 1, 1, all the way to 31st. So we're gonna run that, and then in release, why not? And we got the result, 13 milliseconds for proof generation, and then 1.848 for verification process. And if we take a look at here, a significant difference, but yeah, it all runs. And then last but not least, we're going to check with the fault input, which is over the range. So in this case, we're using a 2 to the 32 bits minus 1. It could be any number as long as it's larger than the Mersenne31. Let's just try with this number. It's going to fail. Yeah, it's gonna fail here. It's gonna constraint had non-zero value on row 0. I think this is the checking of this most significant bit, right? Whether the most significant bit is 0 or 1, and it checked that the most significant bit is 1 instead of 0, so that's why it's failing. And if we use the release mode, it's gonna actually log at the very last stage. So the proof release mode is a little bit different, where we're not strictly checking the constraint that much. We're gonna be able to generate the proof, but the verification process will fail. And yeah, it's verification fail. This is the verification fail logging message that I wrote. Basically the evaluation result doesn't match. That's what it means. And if we just quickly take a look at the source code, this is the expect that I wrote, the verification fail, and it is logging the reasons. All right, so yeah, that's the Mersenne31 example. We cover the error, we cover the errors, some of the traits, and then the constraint itself, and then this is the execution trace, and then prove and verify the Plonky3 backend configuration. So we'll move on to the next one, which is the BabyBear. All right, the BabyBear is a little bit more complex than Mersenne31 because it's not, if you recall, in Mersenne31, the only real thing that you have to check is the first bit, whether if it's 0 or 1. Like it has to be 0, then as long as it's 0, everything else, it could be anything, right? It doesn't matter. But in BabyBear Rangecheck, it's a little bit more complicated than that, because it works on top of a number of 2 to the 31st minus 2 to the 27th. So the largest number will look something like this. Right, the first bit, of course, is gonna be 0. So this is the same condition as Mersenne31, but the most significant bits, the first bit all the way to the 4th bits, they have to, if they're all 1s, then remaining has to be 0. And this is the largest number of this field, and we need to check whether an input sits within this range. All right, let's dive in. So in this example, the reason why we only have 1 row is because we're not using Circle PCS, and it doesn't have a requirement say, hey, your execution trace has to be a certain size or a certain dimension. So this is cleared out for us. So let's jump into the execution trace generation. It's going to be pretty straightforward. You have your value, which is hopefully it's within this range. And then we're going to convert this number into a binary form and then create this one, just like 1 to 32, 1 by 32 dimension matrix. And once we created this, we go to the constraints portion. This is where a little bit challenging, but let's go through the conditions. So the most significant bit in this constraint, it has to be 0. We all agree that. And then we need to check if bits from 2nd to 5th are all 1, then if it's true, then remaining must be 0, right? And we need to also add this extra constraint, say, hey, if this is all 1, then yeah, we're gonna check if it's 0. And then of course, and then we need to check every bit is 0 to 1, and then reconstruct the value matches the input. So first, same thing as the Mersenne31, we need a value input to compare with the reconstructed value. And then we also need to define the width of the execution trace, which is 32. And then we coming back here. This is the constraint itself. Let's explain it step by step. So we have the current row, and then from current row, we're going to compare the very first bit, the most significant bit, making sure this is 0, right? So that's what it's doing, making sure it's 0. And then second, this is the core of this constraint, which is it's going to check, it's going to get a product of the upper bits are the second to fifth, or in this case is the first bit to the fourth bit. Yeah, that one I was counting for 1, but what I meant is like first to fourth. So 1, 2, 3, 4 bits. These, the product of these, I want to get a product of these. And if they're all 1, then the upper bits product is going to be 1, right? If any one of them is 0, then this upper bit product is going to be 0. So that's what I wanted to check. And this is the code that is doing that thing. All right, I also want to get the remaining bits sum, because if the upper bits product is 0, then remaining bit sum could be anything. It doesn't matter. It could be 1, 2, 3, 4, 5, 6, 7, 8, all the way to 27, right? It doesn't matter. But if the upper bits product is 1, then this has to be 0. So it doesn't have to use the product way, but it can use the addition way. So let's come down to here. This is the condition checking instruction where we're going to check, hey, builder, and then when, and it's going to check if this constraint is going to output 1 or 0, and or in this case, it's true or false, right? If it's true, go through this assert 0 portion of the code, and then this will be equal to 0. If it's not true, if it's 0, then the assert 0 will not run. It will just pass, right? And then coming down here, we have this reconstruct the value process. It's the same thing as the Machine31, so I'm not going to cover this. But basically, yeah, reconstructing it, and then compare it with the value itself. So yeah, that's the BabyBear process. Basically, the difference between the BabyBear example and the Machine31 is we added this product portion, and then with this product, we're checking it with the product on result as a condition to do the extra checking. All right, so that's the BabyBear example. And let's quickly go through some of the proof generation process. So just run it here, run it with release. Yeah, it's 17.4 millisecond for proof generation, and then 3.39 for a millisecond. Oh, in this case, actually, the debug mode is faster for some reason. Interesting. But when you're using a debug mode, there might be some additional panic messages. You can ignore them for now. But yeah, in a release mode, normally they won't happen. And yeah, let's just go through a couple more. So this is the max number of the range, which is 0, 1, 1, 1, 1, and then all zeros at the end. And this we should get. All right. So this is the verified result, all that. It went through. Let's use the release tag just so for a cleaner result. All right, yeah, the proof went through, and then the verification also went through as well. All right, let's try. So this was the max number, so why don't we just add 1 to it? Then the verification is gonna fail, and it's saying, hey, the result doesn't match, because the proof that it generated, it's not a correct proof. That's why the verification process will fail. And if you're in a debug mode, the proof itself just won't, even the proof itself won't be generated. Yeah, it's gonna panic the proof generation process. This is basically saying, hey, your remaining bit sum, your bits from the 6 bits all the way to the 31st bits, the sum of them are not 0. That's what it's saying here. All right, so that's it for the BabyBear V1 example. Now we'll cover Goldilocks V1 range check, and it's gonna be very similar, if I be honest. Very similar to the BabyBear V1 implementation, but instead this time it's a 64 bits number. right? So its Goldilocks field is a 64-bit prime, and it looks like this: 2 to the 64 bits, 2 to the 64 minus 2 to the 32 plus 1. That's the prime modulus. So the biggest number will be 2 to the 64 minus 2 to the 32. And the number looks something like this. From the 0th bit all the way till 31st bit, it's all 1. And from 32nd bit all the way to the end, it's all 0. So it's a pretty good looking, easy to process constraints, I'd say, when designing a circuit for it or constraint for it. For execution trace generation, it's the same process, but instead of 32, we're using 64 bits. So we need to push in 64 bits of the element and then convert that into matrix. And the matrix will look like something like this: 1 by 64. And it's very similar, as in check if the first bits to the 32nd bits are all 1. Unlike BabyBear, the first bits doesn't have to be 0, so it has one less step. It just checked from the first bit to the 32nd bits if they're all 1. And if they're all 1, then remaining bits will be 0. And also checking every bit is 0 or 1 and then reconstruct the value. So that's the standard procedure at this point. Everybody should be familiar by now. Yeah, so we first define the value inputs, and then we define the width of the execution trace. And then what we do would be defining the constraints. And same process as the BabyBear V1, we'll just be multiplying every single columns. This is a very bad example. It's not a very optimized example, but just to showcase the idea. But we're gonna multiply 32 elements together to get this upper bits product. And then we're gonna have a remaining bit sum, which is just the addition of the remaining elements from 32 bit to 63 bits. All that together will become remaining bit sum. And same thing is conditional. So we're checking if this condition, if the product is 1, then we're gonna assert 0. If not, then we don't assert. And if we reconstruct the value, and then we get the result. We check the reconstructed value versus the original value itself. Right? And we also do a couple of checkings against 100, against the max value, against the value that is out of range. So let's just quickly do that. All right. All right, so this is the max value and it's passing. But as you can see, it has a lot of loggings here. It's because its blow up factor is way too large. I'm gonna cover that blow up factor in a bit, but don't worry about it. Yeah, and then let's try to add one more number, add 1 to the max number, which is out of range. And this is gonna fail at the verification process. Until this point, I feel like everybody should be familiar with the concept now of saying what is Rangecheck in a constraint in a simple way. It's basically breaking down a decimal number or whatever number into bits, and then we're checking every single bits. And as long as we want to check if a number is within a range, then we just check the most significant bits in a very static way. And if it matches the static symptoms, then the remaining bits has to be a certain order. That's the logic behind it. But the way we do it in a constraint, it's actually very wasteful of resources. So we have to think about ways to optimize it. So what are some of the things that we did that we could have optimized, right? So this is where we're going to cover the BabyBear V2 Rangecheck and also the constraint degree comparison. What are the constraint degree and how do we reduce them? Before we dive in, I just want to make sure I cover the questions. Is it completely necessary to have the initial value in binary in the execution trace? I think I covered that a little bit. Yeah, so because for Rangecheck, we have to use bit decomposition and then to compare bits to make sure if a number sits within a certain range. But yeah, you don't really have to use binary. You could use something else. It's up to you. But yeah, why do we need to convert integer to binary? It could be something else too, right? It depends on your number itself, the range itself. And binary usually is pretty straightforward. If certain bits are certain number, then Because for binary, if you want to say if a number sits within a range, then certain bits don't change as long as they're in that range, right? So in ZK constraints, as long as we can find something static to compare equal to, then we can make a constraint out of it. But if it's like dynamic, like it changes for the same status that we want to achieve, if there's like multiple states, then there's no way to construct a ZK circuits or constraints out of it. Right? It has to have a static status that fits all of those like conditions. So yeah, I guess bit decomposition is a pretty good example of implementing it, but you don't have to use binary. But I would say bit decomposition is the most flexible and can fit the more like broader range of numbers in our example in this case. Because it just breaks very nicely. If you look at the very significant bits, they're all ones and remainings are zeros. It makes it very easy to write circuits or constraints out of it. That's why. All right, so now we'll cover the BabyBear V2 range check and the constraint degree comparisons. So I think it's important to deliver this new concept called constraint degrees. And in this case, the degree of constraint in zero-knowledge proof refers to the highest degree of any polynomial constraints in the systems. So lower the degree of a constraint generally leads to a faster proof generation and smaller proof size. So these two benefits is what we wanted to achieve in any conditions, right? Faster proof generation and smaller proof size. Yeah, our goal in designing circuit in this case will be we wanted to have a secure constraints, yes, but we also want to optimize it to lower down the polynomial degrees. And what are the polynomial degrees? Let's take a look at this. How is the level of degree calculated? Degree is calculated by multiplying the numbers of columns used in a constraint, which means if your constraint is designed to have multiplications of elements in different columns or same columns, it doesn't matter. It's best to have less multiplication as possible. Let's take a look at an example. It could look something like this. So let's say if we use the same column to multiply itself by 4 times, then our constraints will have a degree of 4 because it pretty much looks like x times x times x, right? That's degree 4. And then if we use 5 columns to multiply one another and like elements in different columns, that is x times y times z times w times b, whatever. And this we consider as degree 5, right? And so all of these will contribute to a Fry setting called something called blow-up factors. And blow-up factors, basically, it's in relation to the constraints degree. And the relation looks something like this, right? Degree D leads to a blow-up factor by the next power of 2 of D minus 1, right? If we take a look, when the degree is 4, then 4 is pretty much 2 to the 2, right? Then you get a 4. So the blow-up factor is 2. And for degree 5, because 2 to the 2 is 4. 4 is less than degree 5. So it has to fit in by 2 to the 3, so which is 8. So degree 5 is less than 8. So that means the blow-up factor has to be 3 to fit in this kind of constraints. And the higher the blow-up factors, the more costly, the slower the proof generation process takes, and the bigger the proof sizes. That's why we wanted to reduce down the constraint degree so that the blow-up factor is lower, so that the proof speed is faster, proof generation speed is faster, and the proof size is smaller. So that's the whole relations there. All right. And if you don't understand the blow-up factor and the Fry settings, we're going to cover those, the really in-depth ones, in the later chapters. So don't worry too much. Right now, we focus more on the circuit building, the application side. All right. So let's take a look at what was the problem with BabyBear V1, a degree 4 constraint. So in BabyBear V1, the constraint had a degree of 4 due to constraints like this, which is, if we take a look at the execution trace table, right? It's here. We're doing the first column, second column, third column, fourth column. They're all multiplying with one another to get a product of it. So this is the problem, and we wanted to fix this. Because of this, it causes the blowout factor to increase to 2. In Mersenne 31, our blowout factor was actually 1. And in BabyBear V1, the blowout factor was 2. And in Goldilocks V1, it's even crazier because it's 32 elements multiplying one another. So you have to have 2 to the 5th. So that's 32 elements. 2 to the 5th is 32, right? It fits exactly the 32 elements requirement for Goldilocks V1. So yeah, the blowout factor for Goldilocks V1 constraint is 5, which is crazy. BabyBear V2 constraint, we're going to go through it one by one. First thing, what we're doing is the same as the previous one, which is checking the very first significant bits. It still has to be 0. This does not change, and this doesn't affect the performance at all because it's a degree 1 constraint. So we can keep it as it is, but what we're doing is we're swapping this one with something fancier. And here we're introducing something called intermediate variables. So pretty much is what we're doing is as follows. So now we're going to check if bits from 2nd bits to the 5th bits, or if we start counting from 0, then it's the 1st bit to the 4th bits, if they're all 1s. So what we're doing is we're checking it bits by bits. First step, check if the product of the bits 3 and 4 is 1. All right, this is very confusing. I realize this should be 1 to 4. All right, so just to make it clear for everyone, this should be 1 to 4, and then bits 3 to 4 is the product of bits 3 to 4 is 1. All right, the product of bits 3 to 4 is bits 3 times bits 4, so it's degree 2, right? So we're still keeping the degree under 2, which is great. And then we're gonna provide an external constraint input A that is the product of bits 3 and 4. So we're going to calculate the product of bits 3 and bits 4 externally, and then we give the constraint this product result as an input as well. So what's going on? If we look at the code, this is what we're doing. So instead of just passing in the value, to check with the reconstructed value, we're passing in the bits product of bits 3 and 4. We're also passing in the products of bits 2 to 4. So it's 2, 3, 4. The product of it, we're also passing it here as well. We're also passing in the bits product of 1, 2, 3, 4. And we'll explain why we're passing 3 of these in a bit. So the first step, we're passing in this external constraint input, let's say A, which is the product of bits 3 and 4. We calculate externally. And we're going to reconstruct the product and a constraint, which is from our execution trace, we're going to do a product of the column 3 and column 4. And the product result, we're going to do a assert equal against the external constraint inputs. Right. So if we look at the code, it looks something like this. All right, this is we're checking the very first significant bit, make sure it's 0. And then we come down to what we were covering just now, which is we're going to check if the most significant bits, the product of bits 3 and 4 that is calculated from externally, if they're the same as the product, the constraint computation, the constraint product that we calculated inside this constraint. So it's the 4th bit and the 3rd bit. If they're the same, what does it mean? It means this can be used. This is verified. This is proven that this input is correct. This external input is correct. So that's the stage that we wanted to achieve. So this step is to ensure A, the external constraint input A, is correct. And then in the second step, what we're going to do is we're also going to check if the second input that we provided, the product of bits 2, 3, and 4, if they are the same. Right? So let's go through that. So what's going on is we're passing in the external constraint input B, and which is externally we calculated it's the product of bits 2, 3, and 4. And then we're going to reconstruct the product in constraints. But this is the clever trick part. So instead of multiplying bits 2, 3, and 4, which is going to create a degree 3 constraints, right? That's not what we want. But instead, we are actually going to multiply the input A that we verify in the previous step. And this is an input. This is not a variable. This is a fixed static input. And we're multiplying this fixed static input against bits 2. Right? So we're using these two together is A, and then we're multiplying that with the column 2. Right? So what we're getting in this case will be we're checking the public input B, the external constraint input B is correct. Right? It's verified that it can be trusted. So therefore, by doing this, we reduce the degree. Instead of having the constraint degree to 3, we reduced it down. We kept it as 2. And we're going to do the exact same thing for the last bit. And what's going on is instead of multiplying 1, 2, 3, 4th bits, we're going to use the public input B and then multiply it with the bit 1 and then compare it with the public input C. So this will still keep the constraint as degree 2. So see the trick here is what we did is instead of just multiplying all of them together at once, we're using some external static states, but verify the external static states is correct, and then utilize that in our constraint to reduce the degree. And that's what is called the intermediate variables, intermediate states. So the external states, once they're verified, they can be used in our constraints and reduce the degree significantly. And at last, this is where we're going to check if all bits from 1 to 4, right, not 2 to 5, 1 to 4 are 1. And it is where we just need to check if C, the external input C, is 0 or 1. Right? If it's 1, that means all inputs from 1 to 4, they're all 1. Otherwise, if it's 0, then the remaining bits could be anything, right? So this is the conditional thing that we're checking. And yeah, the remaining is the same. We're checking if C is 1, then the remaining bits will be 0. If C is 0, then remaining bits could be anything. And then also make sure each bits are 0 or 1, and then reconstruct the value as well to compare. And that's what we're going to do. So this is the clever design, right? This is using the public intermediate states, intermediate variables to reduce the degree from 4 to 2. And then this is the remaining bits sum. And here, this is where we check whether if C, or in this case, the most significant byte decomposition from 4 to 1, if it's equal to 1 or 0. If it's 1, then we check the assert 0. If not, we don't check it. And then at last, we check the reconstructed value if it's same with the original value or no. And that's it for the constraint. And then let's take a look at the results. And additionally, of course, we do also need to update our Plonky3 configurations, right? First thing is we need to be able to generate some of these inputs, the inputs for the constraints, because we're not just passing in the variables now, we're also passing in these bits. This is just how I design it. You can design it that your inputs generation process as flexible as you want. This is just an example. And then I'm using this generate trace and input function to generate all the execution trace and the inputs for our air constraints. And then I'm passing all of them in when I'm instantiating it. Right, it's a pretty long name. I realize it's fat. And yeah, the fry config, one thing to know, it's not degree 2 anymore. Now it's degree 1. So it got smaller, it got faster, which is good. And let's take a look at the test result. Compared to the BabyBear V1 and V2, the performance actually improved quite a lot. The degree 2 version is, a lot of them are, as you can see, this is the column that is the degree 2 version. There's the column for the degree 1 version. Yeah, so significant improvements, I'd say. Yeah, you can take a look at it later yourself and try it out. So that's about it for the constraint degree design thinking and how you can do what you can do to improve your constraints efficiency. To really conclude, range checks are pretty important in zero-knowledge proof. This is a slight taste, a simple taste of the implementation. There are multiple ways of implementing it. we're just using one role. There could be multiple roles as well. It's totally up to you on how to design it. Depends on your field, depends on the range that you're working with. There are different ways of implementing it. So yeah, just try out different stuffs. And I do wanted to encourage people, if you wanted to try implement your own version after going through this tutorial, I specifically didn't implement the Goldilocks V2 range check. There are multiple ways of implementing it. This is basically a little assignment for you guys to try out. Yeah, if you're interested, create one and submit a PR. I'm more than happy to review and then even accept that as one of the solution answers too. So yeah, that's about it. Thank you so much.